Matt Roscoe here at the University of Montana, a lecture on the second derivative for our Calculus for Middle School Teachers course. Today what I want to talk to you about is what is the second derivative and use an opening example to teach that idea. And then we'll go ahead and talk about how we annotate or symbolize the second derivative, and we'll definitely take a look at the two alternate notations that you were introduced to in the last section, the Newtonian notation and the Leibnizian notation for the second derivative. And then we'll formalize what the opening example teaches us, that is the second derivative function. What does it tell us about the graph of a function? In effect, what does it tell us about how the function is changing? And then lastly, we'll just do a short application problem and talk about how the second derivative can be contextualized in an application setting. So let's start with an opening example. Let's consider the function 1/5 times x minus 2 times x plus 2 times x plus 6. We'll sketch a graph of the derivative and then use that to sketch a graph of the second derivative, and then ask the question, what does the second derivative provide in terms of information about the graph of the function itself? So let me get out of here and get into the ElmoCam and take a look at what's in store for you. So this worksheet's available on the website for a course, and you're encouraged to follow along. So this is the graph of the function. F of x is equal to 1/5 x. What was it? Let me just make sure I've got it. X minus 2, x plus 2, x plus 6. Some things we notice right away, of course, we're given the zeros of the function when it's written in unfactored form, so we would expect a 0 at 2. Indeed, it's there. Another 0 at -2, and another 0 at -6. If we multiplied this function out, distributing each of the linear factors, we would expect this to be a cubic function, something with an x to the third term, and we see a graph, of course, of a standard graph of a cubic function. And so what we're after at this point, using just measurement, is to try to find out, well, what does the graph of the derivative look like? And then, and maybe not an equal sign here, because we're building intuition about algebraic rules, which will come in the next chapter. But let's take a look at what the graph of the second derivative looks like down here. So get a graph of the first derivative first. How do we do that? Well, this is a good review of the first lecture. I'm going to just choose points along the function and then estimate the slope of the function at those points. I'm going to choose the points at integer values of x just for convenience sake. So these points are the ones I'm going to choose to try to estimate the graph of the function, the rate of change of the graph of the function, and to plot those rates of change down here, because that, after all, is what the derivative is. A few things that I do notice is that we do have a 0 value of the slope right here and right here. So I'm going to go ahead and include those right away as places where we would expect the graph to pass through the x-axis, the graph of the derivative, I should say, to pass through the x-axis at that point and at that point, because of course we have a horizontal tangent line to the function at those 2 points there and there. Okay, well, let's take a look and see what's happening at -6. At -6 we have a positive slope. I roughly go over 1 and up 1, 2, 3, 4, 5, 6 and change. So at -6 we're up at 6 and a little bit more, maybe somewhere in there. Let's see, at -5 the slope is still positive, but it's lessened. It's decreasing. So if I start right here, I would go over 1 and up 1, 2-ish, so somewhere in the neighborhood of 2. Let's see what's happening then at -4. At -4, we've gone through the horizontal slope that we already put down there, and now we're at a negatively valued slope. So the tangent line would look something like that. And it looks like Well, one way we could calculate it would be to go down 1, 2, and over about 1, 2. So it looks like it's about at -1. Then let's go to this next one when we're at x equals -3. The slope of the function looks like we could go down 1, 2, 3 over 1 1/4. So let's see, rise would be -3, run would be 1 1/4, somewhere in the neighborhood of -2.4-ish, so somewhere in here. Let's go to -2. There, the function seems to be very steeply negative, or as negative as it seems to achieve. 1, 2, 3 over 1, so down 3 over 1, so somewhere in the neighborhood of -3. Let's go to this one next and take a look. So something like that. This is at x equals -1. What's the value of the slope of the function? Maybe it'd be easier to see it for you on the screen like that. So let's see, the graph of the function goes over 1 and down 1, 2.5-ish. So 2.5, roughly at 2.5. Let's see what it's doing at 0. When x is 0, we're right there on the function. And I'm just putting a tangent line to the function in, and it looks like roughly over 1, down 1, so a -1 would make sense there. I'm seeing a nice curve here coming to light. We're at 0 when we're at roughly x equals 1/2, but let's see what happens when x is equal to 1. When x is equal to 1, our graph looks something like that. Up 1, let's go up 1, 2, 3, 4 over 1, 2.25. So 4 is our rise, 2.25 is our run. So it's about 1 3/4, somewhere in here. Let's see, when I'm at 2, pretty steep slope right there. Let's see, we'll go up 1, 2, 3, 4, 5, 6-ish over 1. So it looks like we're roughly at 6 when I'm at 2. So something like there. And when I'm at 3, I'm going to be at that particular point. Hard to estimate without the rest of the graph showing, but I would say it's a very high slope. I can see I'm running almost the whole length, which I think this turns out to be 14 so somewhere in the neighborhood of 14 and running just 1 from what I can tell from my ruler. So it looks like past this I'm off the chart in terms of the value of the slope. So our graph of the derivative looks pretty indicative of a parabola. Let's go ahead and sketch in the points. Enlarging the points as needed to make the function seem smooth as we can get it. So something like that. So if up here we have the graph of f of x, or y equals f of x, and down here we have the graph of f prime of x. Okay, so something like that is our derivative function. Now the question is, how do we find the second derivative? Well, the answer is actually quite easy. We can just do what we did here to get the first derivative, again here to get the second derivative. So in other words, we find the slope function that tells us how the slope is changing of the first derivative. That's the second derivative. So we simply iterate the process one more time to get a sense of what it looks like in the second derivative. So let's do it again. One thing I should note right away, it looks like right here at x equals -2-ish that we have a spot where the value of the second derivative, that is the rate of change of the derivative, is valued at 0. The reason I think that is because if I drew a tangent line to the function right there, it would be horizontal, and a horizontal line has a value of 0. So right away at 2, I'm going to put in a value of 0. Okay, and then we'll see what things happen before and after that. So at -6, I'm seeing a steep negative value of the slope of the derivative. So it looks like I'm going to go over 1 and down 1, 2, 3, 4, 5, 6, 7, 8-ish. So I'm really kind of off off the charts. I'm down here somewhere-ish. Okay, well, let's see what happens when we get to -5. Here the value of the function is somewhere, or the value of the slope is definitely negative. Let's go over 1 and down 1, 2, 3, 4-ish. So we're somewhere in the neighborhood of -4. Okay, let's go to the x equals -4 and ask what the value of the slope is in that neighborhood. So it looks like kind of over, let's see, over 1 and down 1 3/4, something like that. So -1 3/4. Let's see what it's at -3. So if I sketch that, it looks like I'm over 1, down a little less than 1, maybe 3/4. Okay, so 2, we think we're at 0. At -1, let's see what happens there. So there I'm going, it looks like up 1 over 1, roughly 1. It's roughly 1. Okay, let's try this one. Here we would, at 0, our slope looks like it's going up 1, 2 over 1 1/4. So 2 divided by 1 1/4. We get about 1.6. Okay, let's try 1 now. Now when I'm at 1, what's going on? I'm going up 1, 2, 3 over 1 and maybe 1/4. So 3 divided by 1.25, it's about 2.4. And let's go to this last one at the value of x equals 2. Let's see, looks like easiest way is going to be to start right here and say I'm going up 1, 2, 3, 4 and over 1, so somewhere in the neighborhood of 4-ish. And that seems to be what we're getting, some sort of shape like that. It is a little bit interesting that everything seems to be fairly linear except for this particular point. So I'm going to just go back and remeasure just to make sure I agree with my original assessment. So if I look at the slope of that one, boy, and you can see how this one is going to be error prone because small changes in the steepness of that line are going to lead to great differences in the value of the slope. So let's just try that. Over 1, down 1, 2, 3, 4, 5, 6, 7-ish. Oh, that's -6, sorry. So it was this one, that -5, that we were really interested in. So let's try that. So at -5, I'd say that's roughly the slope right there, over 1, down 1, 2, 3, 4. Yeah, I still am getting about -4-ish, so I'll just put it in. But we have roughly a graph that looks somewhat linear here, and I'll just sort of draw in a rough estimate of what we have for the graph of the function f double prime of x. So roughly that. And let's talk a little bit about what it tells us. So the thing I hope you're thinking about is, well, you know, this function here tells us when the slope is positive and negative of the function itself. So slopes are all positive in along here until I get to this top. At this point, our slopes change to negative, and we're all negative until I get to this spot, right there, and then the slopes become once again positive as I move up the function in this sense. So a positive, a negative region of negative slope in between here and here, and then a positive region of slopes in between here and here corresponding to positive values for the derivative. So the question is well, what does the second derivative tell us? Well, it tells us when the value of the derivative is either negatively valued or positively valued, right? So how does that translate then into the graph above? And so maybe what we should do is we should just color in where the second derivative is positive, it's in this region, and where the second derivative is negative, and it's in this region. And then just go up to our graph and think about, okay, what does that tell us about the graph of the function? So the value that it changes from negative to positive at is roughly at -2, so roughly at -2. So it's saying something about that part of the function and changing to this part of the function. And the thing I'm hoping that you will notice is that it's telling us about the concavity of the function. So if it's negative, then it seems to be the pink region of the graph concave down. And if it's positive, this is the second derivative, the second derivative is positive, it seems to be concave up. And now we should ask ourselves why that would make sense. So if the second derivative is telling you about how the first derivative is changing, then what it's telling us is how the slopes of the first derivative are changing. So in this sense, the slopes of the first derivative, if we want to think of them, the slopes of the first derivative are all positive here, and they keep decreasing until they get to here. Do you notice that? The slopes are positive, but they are decreasing. I decrease, 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 decrease till I get to here, and now you decrease some more until I get to here. But at that point, at that 2, the values of the slope now slowly start to increase. I know they're negatively valued, but they're growing towards 0 till that point, and then they grow towards a higher number in that region. So in a sense, what the second derivative tells us is the rate at which the slopes are changing. So are they increasing or decreasing? They're decreasing until they get to here, and then they're increasing across this interval. So that really translates into concavity in the graph of the function. So if the slopes are decreasing, then the thing has to be concave down because they are bending downward, right? If the slopes are decreasing, then they have to be concave down because slopes are bending downward. If the slopes of the function are increasing, then they must be concave up because they are slowly bending upward with every successive value of x. So that's really what I'd hoped you would see in this opening explanation, that the second derivative tells us about the concavity of the function. Let's go ahead and escape out of here for now and put this away and talk a little bit about the alternate notations. So you already have seen me use this notation, the notation associated with Newton, the f prime notation. Well, for the second derivative, you just add another prime. Now, if you're evaluating that second derivative at a point, finding the slope of the first derivative at a point, then that second derivative at a point would be f double prime at a. We use a squared symbol, or a 2, in the exponent position in between the d and the y in the Leibnizian notation, and the other square after the x. And of course, this horizontal bar means evaluated at x equals a. So Newtonian notation here on the left, Leibnizian notation here on the right, both mean the second derivative at the point x equals a, evaluated at a point. For the derivative function, if we're talking about, what is this function in terms of its algebraic definition or its value at any value of x, we simply call that f double prime of x, or the second derivative of f at x. And here we would say the second derivative of y with respect to x on the right-hand side. Again, Newtonian and Leibnizian notations for the same thing, the second derivative function. I should, by the way, say the second derivative function here. I notice that's kind of a typo. Okay, so let's generalize. If we know that the second derivative is greater than 0 on an interval, then f prime of x is increasing on the interval, so the graph of f of x is concave up on the interval. So a positive second derivative indicates a region of concavity that is upward in its direction. Now, if the second derivative is less than 0 on an interval, then we can kind of think that the first derivative is decreasing on that interval. So the graph of f of x is concave down on the interval. It's bending downward on that interval. This is a reversible implication, so you can actually do this the other way. If we have a twice differentiable function and the graph of f of x is concave up on an interval, then we actually know that the second derivative will be greater than 0. If the graph of f of x is concave down on an interval, then the second derivative is less than 0. So it's a two-way implication if it works both directions. So, an application here, just think of it this way. If you're given a function that relates two variables, the first derivative tells us about the rate of change of the function itself, but the second derivative provides the rate of change of the rate of change of the function. So the rate at which the rate of change is changing is really what the second derivative tells us. So an interesting contextualization might be to take a look at something we're all sort of somewhat familiar with, I suppose, and the idea of this price of stock. So let's read the prompt. Suppose that P of T represents the price of a share of stock of a corporation at time T. So P is the price, T is the time. What do each of the following statements tell us about the signs of the first and second derivatives? So we have 4 examples here. Let's talk about what those tell us. So let's go back to the video, sorry, not that one, this one. I'll get rid of this. So we'll try to do this in side-by-side fashion. I think I can make it big enough for you to see. So why don't we use the white side, and let's talk about what we know. So for number 1, the price of the stock is rising faster and faster. So let's think about this. If we had P of T on the y-axis, time on the x-axis, let's just draw all 4 of these. I think graphically is the best way to explain it or to think about it. So we seem to be visual learners almost always, at least initially. So let's try that first. And then let's see, 4. All right. So let's draw the first scenario. The price of the stock is rising faster and faster. So if I had a price of a stock, let's say it starts right here, it's rising, so it must be increasing, but it's rising faster and faster. So what it rose in the first period must be quicker in the second period. So I think that means something like this. The price of the stock is rising faster and faster. So let's talk a little bit about what that means for the derivative. To me, what that means, well, first of all, the first derivative, f prime of x, has got to be greater than 0. We know that the price is increasing, so the rate of change must be positive, but it's rising faster and faster. In other words, the rate of change of the rate of change, the second derivative here, and I should probably let's use the notation I've given you, right? P prime of t is greater than 0. So the second derivative would have to be the rate of change of the rate of change is actually increasing because it's rising faster and faster. So the second derivative would have to be also greater than 0. So here we see a case of a graph that's both increasing and concave up, right? So we could think about that as a way to contextualize. So increasing, and I'll use CCU. Maybe I'll just get rid of the parentheses and do it up here, increasing and concave up. Okay, so let's go to the second one. The second one says the price of the stock is falling more every day. So the stock is falling. So what it falls in the first day, it will fall even more in the second day and even more in the third day. So we have something like this. So something like a function that's falling more and more every day. So the acceleration in falling is increasing. So let's think about that. So it's a decreasing function and it's concave down. So if it's a decreasing function, we know that p prime of t is going to have to be less than 0 because the slope of the function is negative. And the slope of the function is actually getting more and more negative, right? So the second derivative would have to be also less than 0 because the slope of the function is getting more negative. So sometimes people get confused here that yes, the value of the slope is growing in absolute magnitude, but in a negative sense. So it's getting more negative, meaning it is actually decreasing, right? The value of the slope is going from one negative value to a steeper negative value. So it's decreasing. Concave down as well seems to confirm that second derivative should be less than 0. Okay, so let's go ahead and talk about what's going on in number 3. It says the price of the stock is topping out. So I think we can all agree that this would be something like this. The price of the stock is topping out. So we have an increasing function, right, which is concave down. So if it's an increasing function, we know that p prime of t is going to be greater than 0. If it's concave down, that means that the increases are actually decreasing, right? The increases are decreasing. So the rate of change of the increase is slowing. It's decreasing. So the second derivative should actually be less than 0 because it is decreasing. The slopes are decreasing as we move forward in time. So here's a case where the first and the second derivative have different signs, increasing at a decreasing rate. And then the last one, the price of the stock is bottoming out. So the stock would have something like this. Here we would say this is a decreasing function. So it's definitely the function is getting, the value of the function is decreasing across the interval, but it's concave up. So it's decreasing, but at an increasing rate. The slopes are definitely negative, but they're growing closer and closer to 0, so they're rising in value. So we would think of this as something that's less than 0 for its first derivative, but greater than 0 for the second derivative. So I hope that gives you an idea of these are really the 4 ways that the first and the second derivative can interact in terms of their absolute values or their signs. Sorry, I shouldn't say absolute values, but their signs. You can have both positive and you get an increasing concave up graph. You can have both negative, you get a decreasing concave down graph. Or you could have one positive and one negative. In those two cases, you get either an increasing graph at a decreasing rate, which is a concave down increasing graph, or you get a decreasing graph at an increasing rate of change, and that would be a decreasing graph concave up. Okay, well, I hope that this gives you some idea of what the second derivative is and what it tells us, and I look forward to hearing your questions, and let me know if you have them.